Here's another video to the lecture intropde. In this video we present section 5.7. And this section, in this section we will solve the inhomogeneous wave equation in all dimensions. We will apply a simple method which derives the solutions of the inhomogeneous wave equation in terms of homogeneous solutions, in terms of solutions of the homogeneous wave equation. So this is called Duhamel's principle. This method which derives solutions of inhomogeneous linear PDE in terms of the corresponding linear PDE. And again, this is quite an easy application by considering the wave equation as a first order linear PDE on pairs of functions which depend on x. In fact, we may write it in this form here. So the derivative of this pair of functions depending on x and with respect to t. So we consider the solutions as functions depending on x and on t. And so this means we consider this as families of functions depending on x which depend on t. And then if we take the derivative of these two pairs, then this is clear. The derivative is just, of course, of the first component is just the second component, and the inhomogeneity is doesn't give any contribution for the derivative of the function u, and the derivative of the derivative, so of the second component. This is, of course, Laplacian of the first component plus the inhomogeneity in the second component. So this is, now we have transformed it into a linear ODE. So this is the linear operator and this is the inhomogeneity. And then if we now apply the method of variation of constants in order to obtain the corresponding inhomogeneous special solution. So we now want to calculate the inhomogeneous special solution of this linear ODE, and we know this we obtain by inserting the inhomogeneity as an initial value problem. So let's do this. So we so in order to calculate this special inhomogeneous solution of the inhomogeneous wave equation, with initial value 0, we define a family of homogeneous solutions where the initial value is given by the inhomogeneity. So this is the initial value is given by the inhomogeneity, and since f is only the component of the second since this is the inhomogeneity, so f is only in the second component. This means it should be the initial value of the derivative, and the initial value of the function itself should be 0. Since here in the inhomogeneity we have in the first component 0. Okay, so we define this initial values in general at s, and for time s, and this is the extra parameter of this solution. Then and the derivative of u, so the initial value of the derivative, the first derivative with respect to t. Here you see this component has initial value f. So we define this, and then the integral, the integral over s from 0 to t now solves indeed the inhomogeneous wave equation. And this integral is clearly, if we set t equals 0, then it's an integral over a function over an interval of length 0, so this is 0. So this is clearly vanishes at t equals 0. But now we can calculate this this second derivative. We calculated by the fundamental theorem of calculus for this integral. We have two places where this depends on t, at the integral, at the upper bound of the integral, and here inside of t. So we get two contributions. If we here at this place we may use the fundamental theorem of calculus, so this means we should insert s equal t. So we get this term for the first derivative, and this is the other term by taking the derivative. So this sum is clearly the derivative of u of x and t, and now taking the second derivative, then we should keep in mind that this term here is 0, so this term here vanishes. So we only have to calculate the second derivative of this term, and again we get two contributions. We get on the one side the second, so now we get two contributions. Again we get by the fundamental theorem of calculus, if we take here the derivative, then we get this expression here, and if we take here derivative, then we can put the derivative inside the integral, and we get this. And then of course we know the second derivative is the Laplacian, and this value is by definition x of t. So we get this expression, but this expression is clearly the Laplacian applied to this integral. So we indeed solve the inhomogeneous wave equation. If we subtract this Laplacian, then we just get the inhomogeneity f. So this shows that we really get the inhomogeneous wave equation by this formula, or by Duhamel's principle. And then the whole initial value problem for the inhomogeneous wave equation, where we fix the initial values, is clearly this special solution here. This is a special solution with initial value 0, but of the inhomogeneous wave equation, plus the solution of the corresponding homogeneous initial value problem. So in this sense, the Duhamel principle reduces the solution of the inhomogeneous equation to solutions, or derives solutions of the inhomogeneous initial value problem in terms of solutions of the homogeneous wave equation, like the method of variation of constants for ODEs. And now, finally, in this chapter, we also want to investigate how the present determines the past for solutions of the wave equation. Okay, what does this mean? The wave equation is invariant with respect to time reversal. This is clear, since we only have second derivatives, and of course first derivatives change their sign, but second derivatives are unchanged. So the first derivative changes sign, and therefore the values of u of the solution of the end value problem. This we mean by how the present determines the past. So we look for solutions for negative times if we fix the values for time 0. So if we fix the present, how the past looks like for the solutions. And we do it immediately also for the inhomogeneous equation. Now, since time reversal doesn't change the equation, it's quite simple to solve this equation. Yeah, one only have to take into account that the first derivative changes sign. So this term here, this changes sign. So we look for the solutions with initial values g and h reversed, so minus h, and of course inhomogeneity we transform just by time reversal, and then we obtain a solution of this initial value problem, and now we insert negative times, but we insert positive times in this solution, but for negative times. So we take the negative of a negative time, which is a positive time, and insert this into the corresponding initial value problem with values g and minus h. And with f, in f replace t by minus t. Then by this behavior under time reversal, we directly see that this now solves this equation. So this means for the wave equation, the present not only determines the future, but it also determines the past. And of course, we may combine these two solutions, so the solution of this end value problem and the initial value problem, to obtain a solution on the whole for all times t. Okay, so what have we done today? We understood how we transform with Duhamel's principle, how we calculate solutions of the initial value problems in terms of the inhomogeneous wave equation, in terms of solutions of homogeneous wave equations. And we saw that we directly can apply the method of variation of constants of ODE to this linear PDE. And then finally, we also investigated the behavior under time reversal. Thank you.